Hello everyone, I'm Divya, your maths facilitator. So in this class, I'm going to discuss the very important concepts of chapter number 1. Now these important concepts, I'm going to discuss in examination point of view, competitive examination point of view. Okay, so we are going to revise all the concepts of this chapter very quickly, right? And we'll be covering the most important points of this chapter, right? So this video is going to be very important for you if you're going to start preparing for your competitive level examinations, right? So let's begin. So firstly, real numbers chapter consists of different concepts and but I just want to start from the basic. Okay, so basically we all know that numbers are divided into rational numbers, okay, and irrational numbers. Okay, so if you take the combination of rational and irrational, okay, rational plus irrational numbers will give you real numbers. Clear? So rational numbers plus irrational numbers will give you real numbers. Now what are rational numbers? Rational numbers are the numbers which are of the form p by q. Okay, in simple words I can say which are of the form of fractions. Okay, numerator and denominator p by q form में होना चाहिए, and where this p and q belongs to integers. Okay, p and q can be any integer, and this q should not be equal to 0. This denominator should not be equal to 0. Why? Because if the denominator is 0, then that particular rational number becomes undefined, isn't it? So anything divided by 0 becomes undefined. So hence our condition is the denominator should never be equal to 0. So this is a rational number. And one more important thing is natural numbers, whole numbers and integers are all subset of rational numbers, and rational numbers you can denote it by q. Right, beta? Now, if I have to talk about irrational numbers are something which are not rational, okay, which are not rational, or I can also call this as irrational numbers are numbers which cannot be expressed in the form of p by q. Okay, so now any number which is not rational is irrational. So all the rationals plus all the irrationals together, put together, you get real numbers. Clear? Okay, and one more important concept, let's discuss here itself. So rational, and you have irrational number. So now if you want to convert a rational number to a decimal form, okay, if you want to convert a rational number to a decimal form, you actually can do it in two ways. Okay, any rational number can be converted into decimal form, right? You can divide and convert it into decimal form. Suppose you have 1 by 3, this is a rational number, you can convert it into decimal form. So if you convert it into decimal form, you get something like 0.333 and so on. And suppose if you have 1 by 2, this is also a rational number. If you convert it into decimal form, you get something like 0.5. Okay, 0.5 is a decimal and 0.333 and so on. Endless. Okay, the decimal is not coming to an end. So this is also a decimal number, but we call this as a terminating decimal. Why? Because here you can see the decimal place has an end. It is terminating here. And here the decimal place is not terminating. It is continuing. Okay, there is no end to it. So we call this as non-terminating. Okay, so any rational number, when you convert it into decimal form, you can either have a terminating decimal or you can have a non-terminating decimal. Clear with this point? But let me also clear this concept that in a non-terminating decimal, here you can see the number is repeating, the decimal is repeating, 333, it is repeating. So whenever you convert a rational to a decimal, if it is non-terminating, if it is a non-terminating decimal, then it is also a repeating. Okay, you call this as non-terminating repeating decimal. Clear? So let me conclude it here. So rational number, when you convert it into decimal, you either get a terminating decimal, okay, or you get a non-terminating decimal. Okay, it is non-terminating, at the same time it is also repeating. Clear with this concept? Okay, now what about irrational number? If irrational number is always of the form non-terminating, okay, it is also non-terminating. So now here you can see rational number is non-terminating, irrational number is also non-terminating. So where is the difference? Rational number can be a non-terminating, but it is a repeating. Okay, it is a repeating. Irrational number is non-terminating and it is non-repeating. Okay, non-repeating, or you can also call it as non-recurring. So irrational number is non-terminating as well as it is non-repeating or non-recurring. Okay, so non-repeating or non-recurring. So I call it as NTNR, non-terminating, non-repeating is called irrational, and NTR, non-terminating, repeating is called rational, and rational can also be terminating. Okay, these are the two types of decimal conversions of a rational number, and irrational is always non-terminating, non-repeating. These are the basics. I hope the basics are clear. So after this, the next concept we jump into is Euclid's division lemma. Okay, now what is Euclid's division lemma? You don't have to worry with the statement. It is very simple. So suppose if I have two numbers, okay, if I have 2 divided by 3, so 6 divided by 2, I have taken 6 divided by 2, so 6 divided by 2 gives me 3. Okay, in simple division form, if I can write 2, so 2 3s are 6, I get a 0. If I want to divide 7 by 2, how will I write it? 7 by 2, so 2 3s are 6, my remainder is 1. Clear? So Euclid's division lemma is nothing but, so here you can see this is my dividend, this is my dividend, and this is called divisor. This is what we have learnt in our lower classes. This is called quotient and this is called remainder. Similarly here also this is called dividend, this is my divisor. Okay, this is my quotient and remainder. So always, now suppose if you denote the dividend by a, okay, and I'm denoting the divisor by the letter b, and quotient I am denoting it by Q, and remainder I am denoting it by R. Okay, so dividend I am denoting it by small a, divisor by B, quotient by Q, and remainder by R. Okay, that means dividend is A, divisor is B, quotient is Q, and after dividing you will get a remainder R. So the relation here you can see is always, let me change the color. Yes, here the relation you can see 6, this dividend I can write it as 2 times 3. Okay, divisor into quotient, 2 times 3 plus the remainder. Okay, 6 I can write as 2 times 3, 2 3s are 6 plus the remainder. Okay, here also this 7 I can write it as, see here, 2 3s are 6, 2 times 3, divisor into the quotient, divisor into the quotient plus the remainder. So 2 3s are 6 plus 1 gives me 7. Similarly, here also I can write, here also I can write. So this dividend I can write it as divisor multiplied by my quotient plus the remainder. Clear? So the same thing, देखो, A is equals to BQ plus R is what is called Euclid's division lemma. Clear? Okay, so where A is the dividend, B is the divisor, A and B are any two positive integers, dividing them, okay, you get unique integers Q and R. Q is nothing but quotient, R is nothing but the remainder, and the relationship between these four is nothing but A is equals to BQ plus R, which is nothing but dividend is equals to divisor into quotient plus the remainder. Okay, I gave you the examples also to understand, right? And in each case you can see that, this remainder which you are getting is always either 0, either it is 0 or it is a number which is less than b. Less than b means it is less than divisor. Remainder is always between 0 and the divisor. Is this clear? You can check number of examples. So here you can see this my remainder. My remainder in these two cases, one time it was 0, the other time it was 1. That means my remainder was 0, less than or equal to it. It was either 0 or it was less than or equal to my divisor. Divisor was 2. Isn't it? 0 less than or equal to R less than, my divisor is 2. So between 0 and 2, how many numbers I have? I have only 1, 0 and 1. Okay, it can be equal to 0, and between 0 and 2 I have only one number, that is 1. So my remainder in each case, if I am dividing a number by 2, my remainder can be either 0 or 1. That means my remainder is always satisfying this condition. Okay, it is between 0 and the divisor. Clear with this? You can take any number of examples and check this. Okay, and we are also taking my divisor is greater than the, sorry, my dividend is greater than the divisor. Okay, this dividend is greater than the divisor. Only then you can happily divide, otherwise you get a decimal value, isn't it? Chalo, let's move on to the next part of Euclid's division lemma. Euclid's division lemma, this is what it is. So there is an application to Euclid's division lemma. You can find HCF, highest common factor, using Euclid's division lemma. Clear? So how do we do that? We use Euclid's division algorithm. Now what is the meaning of algorithm? Algorithm is nothing but a series of steps, or I can say a sequence of steps. Okay, so sequentially, let me put it this way, sequentially, if you are using Euclid's division lemma, you will get your HCF. Okay, so that means if I am using Euclid's division lemma in the form of algorithm, okay, sequential order, I'm going to get my HCF. So let's find how are we going to get this. So this 721 is the bigger number, so you can take A as 721, which means my dividend is 721 and my divisor is 595. So if I divide these two, I'll get my quotient and the remainder, isn't it? So 595 one times gives me 595 and my remainder will be, if I subtract, it will be 6. Okay, so here it will be 2 and 1, 126. Okay, so let me write this particular division in form of Euclid's division lemma. I know that my dividend is equals to divisor into quotient. So 595 into quotient is 1 plus my remainder is 126. So in the next step, what do you do? In the next step, you take this as the divisor. Okay, ये जो 126 है, you take this as a divisor and this 595 will be your new new dividend. Okay, so this 595 will be the new dividend. This 126 will be my new divisor. So I write 595 is equals to 126 into, I don't know my quotient and remainder, so I have to divide now. So if I take 126, how many times will I get this? 126, how many times will I get this? 126 into, if I take 4 times, okay, so 126 4 times gives me 8, 10, 504. Okay, so 126 4 times gives me 504 and here I have 191. Okay, 91 is the remainder. Now 91, see, it is less than my divisor, so you stop it here. So multiplying these two, you will get 595. So 126 into 4 plus my remainder is 91. In the next step, what happens, beta? In the next step, what happens? See here. I take this as the new dividend. 126 is the new dividend, that is equals to this 91 is the new divisor. Okay, so let us divide 126 divided by 91. So how much will you get? 91 one times gives me 91 and the remainder will be 35. Okay, so 91 one time, 91 into 1 plus 35 gives me 125. Now what is the next step again? See the next step. Now this 91 will be my new dividend and this 35 will be the new divisor. Okay, let us divide again. So 91 divided by 35, 35 twos gives you 70. So you have 21. So 35 into 2. 35 into 2 plus 35 into 2 plus how much you have here? 21 is the remainder. Clear? So now this 35, let me change the color. Now this 35 will be the new dividend and this 21 will be the new divisor. Okay, so let us divide 35 divided by 21. One time you get 21, so how much is the remainder? 14. Okay, so 21 into 1 plus 14, remainder is 14. Okay, so basically we are applying Euclid's division lemma. This is A is equals to B into quotient plus remainder. This is what we are doing all the time sequentially. Okay, we are following the order. That is nothing but a algorithm, isn't it? So I told you sequential steps you are following, which is nothing but algorithm. Okay, and these sequential steps are based on what? They are based on Euclid's division lemma. Okay, so now here you can see my 21. This 21 will be, I'll write it here neatly. 21 will be the next dividend and this 14 which is there, this will be the next divisor. Okay, so let us divide 21 divided by 14 gives you how much? 14 ones are 14 and how much is the remainder? 7 will be the remainder. Okay, so 14 one time plus 7 is the remainder. Clear, yeah? Now this 14 will be my next dividend, and the 7 will be the divisor, and I know 7 2s are 14 plus remainder will be 0. So wherever the remainder is 0, wherever you are getting the remainder as 0, you stop your division process here, or you stop your process here and compare this with Euclid's division lemma. What do you get? A is equals to B Q plus R. Okay, so whenever this R, this remainder is 0, okay, when my remainder is 0, whatever B value you are having here, by comparing B is 7. So this B value will give your HCF. Therefore, I can say the HCF of 595 and 721 is how much? It is nothing but 7. Okay, so whenever my remainder is 0, I stop the process and I compare it and I take the B value, the corresponding B value or the divisor as a HCF for the highest common factor. I hope this is super clear for you now. Let's move on to the next concept, which is called fundamental theorem of arithmetic. This is the second concept of this chapter. Now, what is fundamental theorem of arithmetic? This is also not at all new to you. It is very simple. I'll explain you in a simpler way. Just see. Suppose you have a number 9, okay, or let's take a little bigger number so that you get more factors. I'm taking a number, say 12. Okay, this 12 I can write it as 4 threes are, okay, or 4. If I want to prime factorize 4, I can write as 2 square into 3. Okay, I'll just do it here, prime factorization. So 12, so dividing by 2, this is what I get. Okay, so I can write 12 as, just see here, I can write 12 as 2 into 2 into 3. Okay, 2 times 2 into 3. Or the same 12 I can write as, if I take 3 first, I will take 3 4s are 12 and 2 2s are 2 1s are. So the same 12 I can write as 3 into 2 into 2. Or the same 12, if I want to do it in another way, can I do it? No, I think only two possible ways we are getting. Acha, because it's a very smaller number. So here you see, okay, so two ways. Now this 12 I am able to prime factorize it in two different ways. Okay, and I know my 12 is a composite number. Okay, you all know that 12 is a composite number, right? Because it has more than two factors. 12 has more than two factors. It's a composite number. Yeah, the clear? Okay, so now prime factorizing this composite number, I am expressing it as product of primes. Okay, 2, 2, 3 are primes, and I have expressed it as product of primes. Clear? So this is a prime factorization. Now if you just observe these two prime factorizations, the prime factorization is unique. Now what is the meaning of unique? Unique means, now see here, how many 2's do you have? In the first case you have 2 2's and 1 3. In the second case also you have 1 3 and 2 2's. That means the number of the prime factors which you get are unique. Okay, how many 2's you have? 2 2's and 1 3. In the second case also 2 2's and 1 3. That means in whichever way you prime factorize, the prime factors are unique. Okay, you get the same prime factors all the time. Okay, whichever way you prime factors, that is the meaning of this. Second point is the order of the prime factors can be different. Now here you can see 2's are first and then last you have 3, and here you can see 3 is first and 2's you have last. That means however you prime factorize, the prime factors are same. That is the first point, unique. First point. Second point is the order can be different but the answer will be same. The order can be different. Okay, so let us read the statement again now. So every composite number can be expressed as, okay, every composite number can be expressed as product of primes. Okay, product of primes, but this factorization, this prime factorization, you can express it as product of primes, but the prime factorization is unique. Okay, every composite number you are expressing it as product of primes, but the prime factorization is unique, which means however you do, you get the same prime factors. Apart from the order, okay, order in which the prime factors occur. That means यहाँ पर देखो, first you have 2's and then you have 3. Here first you have 3 and then you have 2's. That means the order can be different, but the prime factors which you get are same. This is called fundamental theorem of arithmetic. So 2 points you remember. First one is the prime factorization is unique. Second point is the order can be different. No problem. Okay. So every composite number can be expressed in this way. Right. So the next important thing is HCF and LCM using prime factorization method. So whenever you want to find HCF and LCM, so this is what the simple point you can remember. Okay, so whenever I want to find HCF, I take only the common factor. Okay, if I want to find the HCF, I take only the common factor. Okay, and among the common factors, first point is I take only the common factor. Second point is among the common factor, I choose the least power of the common factor. Okay, H ka matlab highest, and here I choose the least power. Clear? Now, if I want to find LCM using prime factorization method, LCM. For LCM, I take all the factors. Okay, for HCF, you are taking only the common factors, but for LCM, you will take all the factors. Second point is, sometimes among all the factors, you can have common factors. So, wherever you find common factors, in the common factor, L ka matlab least. Here, you take highest. Okay, you take the opposite of this. See here, H ka matlab highest, you are taking the least power. L ka matlab least, you will take the highest power wherever you get a common factor. Clear with these things? Okay. Suppose if I want to find the LCM, for example, if you want to find the LCM and HCF of 12 and 15, prime factorizing 12, you get it as 2 6 2 3 3 1. That means 12 I can write it as 2 square into 3. 2 you have 2 times, isn't it? So I can write as 2 square into 3. Now 15 is nothing but 3 5 5 1. So 15 I can write it as 3 into 5. Okay, so now if I want to find the HCF, firstly I am finding the HCF. For HCF, first point is you take only the common factor. So out of these two, you have only one common factor, which is 3. Write 3 as it is. Okay, now second point is you take the least power of the common factor, but here you see the common factor has only one power. Power is same, 1 and 1, so 3 is the HCF. Okay, you take the common factor, and among the common factor, if there is any power, then you choose the least power. Here there is power is 1 and 1, power is same, so there is no choosing anything, so you write the power as it is. So 3 power 1 is your HCF, or 3 is your HCF. Now if you want to find the LCM, for LCM I told you will take all the factors. So 2 is a factor here. Okay, so 2 square you have, write 2 square as it is. Now 3 is also a factor, write as it is. 3 is a common factor. 3 is a common factor. Now whenever common factor you have, you choose the highest power. But here in this case, as I told you, power is 1 and 1. Power is same, so there is no choosing of highest or lowest. So power is same, so I am taking this 3 power 1 into, I have one more factor 5. So this will give me my LCM. Is this clear? So it is 12 5 is 60. Clear? And one more important thing which we have to understand is that for any two positive integers, suppose for 12 and 15 are any two positive integers A and B, LCM, product of LCM and HCF is equals to the product of the two numbers. Okay, that means if you multiply these two, okay, let me do it. Now LCM, now here you see HCF you got it as 60, LCM you got it as, HCF you got it as 3R. HCF is 3 here, just look. HCF is 3. So HCF you got as 3, LCM was 60, and the numbers I'm taking it as A was, first number was 12 and B was 15. Clear till here? So here the condition they are telling you is that if you take the product of LCM and HCF, so LCM multiplied by HCF should give you the product of the two numbers. Okay, so this is what you get. So this is also 180 and this is also 180. Yes or no? Just check. So 12 into 15. 12 into 15 is also giving me 180. Right? Absolutely. Okay. So this is the condition whenever two numbers are given to you. Product of the LCM and HCF of the two numbers is equals to the product of the two numbers. Clear, yeah? Let's move on to the next concept. Now, what about three numbers? When two numbers are given, it was very easy. Now, what about three numbers? If A, B, C are any three numbers, okay, if A, B, C are any three numbers, then HCF, product of HCF of all the three numbers and LCM of all the three numbers, product of HCF of all the three numbers and LCM of all the three numbers, okay. That means multiplication of HCF and LCM of all the three numbers is equals to product of all the three numbers, okay. So similar to the previous question, there you had only two numbers, here you have three numbers. Now suppose if you want to find LCM of any two numbers, if you want to find LCM of any two numbers, acha, 1 second, yaar, 1 second, 1 second. It is not equal to, just look here. HCF, product of HCF and LCM of any three numbers is not equal to the product of the three numbers. Like in the previous case, you have taken product of HCF and LCM. Here you see product of HCF of the two numbers multiplied by the LCM of two numbers is giving you the product of the two numbers. This was it. But here it is not equal. When you take three numbers, HCF and LCM, product of these two and the product of the three numbers are not equal. Clear with this condition? So then how will you find? So here it is. So just see here. So if you want to find the LCM of three numbers, then this is what you do. So product of the three numbers multiplied by HCF of the three numbers divided by HCF of two numbers taken together. Okay. That means now suppose here you have three numbers A, B, C. So firstly you take AB together. Okay. Then you take BC together, HCF of BC. Then you take HCF of AC together. Okay, now if you want to find HCF of ABC, HCF of the three numbers, then you take product of the three numbers multiplied by LCM of the three numbers divided by again LCM of A and B, LCM of B and C, LCM of A and C. Clear with this, yeah? So firstly, if you want to find the LCM, you take product of three numbers multiplied by HCF of the three numbers, okay, divided by HCF of two numbers taken two at a time, okay. Product of HCF of two numbers taken at a time. AB, BC, CA. Similarly, for HCF, what do you do? Instead of HCF, here LCM is replaced. Okay, here, see, if you want to find HCF, you will take the LCM. If you want to find LCM, you take the HCF. Clear, yeah? Clear with this all? Okay, so let's move on to the next one. And then what about irrational numbers? We have already discussed irrational number is something which is not rational, which cannot be expressed in the form of P by Q. Okay, and Q is not equal to 0. So for some examples of irrational numbers are root 2, root 3, root pi, root 2, root 3, pi and so on. And also irrational numbers have non-terminating, they are neither terminating and non-recurring. Non-terminating, non-recurring, NT, Okay, we have discussed this. You will have NT, okay, and root over any prime number. Root over any prime number in general, I can say it is a irrational number. Okay, root 2, root 3, root 5, root 7, anything. Let's move on to the next important theorem of this chapter. If a prime number P divides A square, then P divides A. Okay, suppose I have a prime number, I am taking, for example, I am taking a prime number 3. Okay, if this 3 divides A square, suppose for example, A value I am taking it as 9. Okay, A value I am taking it as 9. If my 3 divides A square, what is A square? If A is 9, A square will be 9 square is 81. Okay, if I am dividing this 81 by 3, okay, 3 divides 81, we all know it, right? Then this 3 also divides 9. Okay, the same statement here I gave you an example. Without example, if my P divides, if P is a prime number, if P divides A square, then P also divides A. Clear with this? Okay, if my P is dividing A square, my P also divides A. Okay, for example, I have taken P as 3 and A as 9 and A square will be 81. You can take any example for that case. Okay, let's move on to the next theorem. Now, suppose if you have a rational number, suppose X is a rational number. X is a rational number whose decimal expansion terminates. Okay, the decimal expansion of X terminates. Okay, that means X is a terminating decimal. Okay, and it can be expressed in the form of P by Q. X is a rational number, it can be expressed in the form of P by Q. And if I convert this into decimal form, my decimal expansion terminates. Okay, then I can say that my Q, my denominator, okay, my denominator Q is of the form, my denominator Q will be of the form 2 power m, 5 power m. Okay, so if I prime factorize my denominator, it should be of the form 2 power m, 5 power m. That means it should have 2 and 5 in the prime factorization. Only 2 and 5. Okay, I am mentioning it here. Only 2 and 5 you should have in the prime factorization of the denominator. Otherwise, other than 2 and 5, if you have any other prime number, it will be non-terminating. That is the next theorem I will tell you. Okay, so if, understand, this is a theorem. If X is a rational number, it can be expressed in the form of P by Q. If it has a terminating decimal, okay, if the decimal expansion is a terminating one, then this denominator can be expressed as 2 power n, 5 power n. That means only 2 and 5 will be the prime factorization of cube. For example, if I take 2 by 10, okay, 2 by 10 is a terminating decimal, you can check it, okay. Then this 10 is nothing but it is q, right? This is p, 2 is p, and q is the denominator, which means here you have 10, right? So this q I can express it as 5 twos are, isn't it? So that means the denominator I am writing it as 5 into 2. So this became a terminating decimal. Clear, yeah? So the denominator, if you can write as 5 and 2s, in terms of 5 and 2s, then it is a terminating decimal. If you have any other number other than 5 and 2, it will be non-terminating. That is the next term. Let's discuss. Now the converse of this theorem is also true. The converse of this theorem is also true. Suppose if you have a rational number p by q, okay, and if it is a terminating, now here we have seen that it's a terminating, so you can write it, q can be expressed as 2 power n, 5 power n. Now I am saying the converse of this, okay. Now the converse is, if p by q is a rational number and q is of the form 2 power n, 5 power n, then I can say that my rational number, the decimal form of this rational number is a terminating, okay. So I'll explain you very clearly here in one step. Suppose p by q is a rational number, okay, and q, okay, let us firstly write the first statement. P by q is a rational number and this rational number is a terminating decimal expansion if this q is of the form 2 per n, 5 per n. This is the original theorem. Now the converse of it is nothing but, if p by q is a rational number, q is of the form 2 per n, 5 per n, then I can say that it is a terminating decimal, okay. Nothing but the reverse of it, okay. In your problem sometimes they may give you it is a terminating decimal, you will find that q is of this form 2 and 5. Sometimes it may happen that you will firstly check if q is of form 2 and 5, okay. If you have 2 and find the prime factorization of q or not, if you have, then it is a terminating decimal, okay. So both we use depending on the situation. Now let's move on to the next theorem. So I have been repeating about this theorem earlier also. So if you have a rational, so if you have, instead of rational number, I'll just rename it as, if you have a number, okay, if you have a number p by q, and if this q cannot be expressed as 2 per n, 5 per n, okay, if you have something like p by q and this q cannot be expressed it as 2 per n, 5 per n, then I can say that this particular number is a non-terminating, okay, it is a non-terminating decimal expansion, okay. So I'll again tell you, if you have a number or a rational number of the form p by q, okay, you're having a rational number of the form p by q, but this q, this denominator q, you're not able to express it as 2 per n, 5 per n, then simple it is a non-terminating decimal expansion. Clear? Suppose the same example 1 by 3 we have taken earlier. This is a rational number, right? But my denominator is 3. My q is 3. Now I told you other than 2 and 3, you should have only 2 or 5. Other than this 2 and 5, if you have any other number in the denominator, blindly mark it as non-terminating decimal. You should have only 2, only 5, or you can have 2 and 5, but other than 2 and 5, no other number is allowed in the denominator. If you have any other number, when you prime factorize, if you are getting any other number in the denominator, then you can conclude that it is a non-terminating decimal. So let me just generalize here all the statements we have learned here in these two theorems. Suppose p by q is a rational number, okay, it will have a terminating decimal if q is of the form 2 per n, 5 per n. The converse of this you have learned, if q is 2 per n, 5 per n, then it will be a terminating. Okay, now I am saying if this q is not of the form 2 per n, 5 per n, then what happens to this decimal expansion? It becomes non-terminating. Okay, clear till here? Now tell me what happens to irrational number then? Irrational numbers, yeah, they cannot be expressed as p by q only. You will not have any denominator. They cannot be expressed of this form. So no theorem for that. But you can understand that non-terminating, non-repeating are nothing but irrational numbers. Okay. So these three theorems, I hope they are clear for you, and I hope you have liked this class. I hope all the concepts are very clear for you now. So within a very short span, I try to explain the entire chapter for you. Right. So I'll meet you all in the next class with a high level questions again. So do subscribe to the channel and like the video and share this channel to all your friends. Let's start our competitive level preparations here, right? So don't forget to subscribe to the channel and like the video, and do comment and let me know how are you, liking it, or if you want any more content in the channel also, you can definitely comment and let me know. Thanks for watching.